If direct substitution does not give an answer to a limit problem because an indeterminate form is obtained, indeterminate, remember things you can't solve like 0 over 0 or infinity over infinity, etc. Use algebraic techniques to change the form of the limit. The limit as x approaches 0 of this function right here. If we plugged in 0, that would make the denominator 0. We would get 0 on the top as well. 0 over 0, can't do it. So let's use some algebra first. What do I notice? X over x, that's just 1. So I can simplify this to the limit as x approaches 0 of 1 over x plus 1. Now I can use direct substitution. At this point in time, I no longer write this limit symbolism, okay? Once you direct substitute, you are actually evaluating the limit, okay? So you don't need this symbolism, and if you write it, it is incorrect. Now I direct substitute, and I get 1 over 1, which is 1. All right, the limit as x approaches 2 of this function, I can actually factor the denominator here, which gives me x minus 2 over x minus 2. So now I'm just taking the limit as x approaches 2 of 1 over x plus 2, and that I can use direct substitution for. 1 over 2 plus 2, that is 1/4. Try factoring number 3. This is perfect cubes, so it factors to be x squared plus x plus 1. All right, x minus 1 over x minus 1 is 1. Now I can direct substitute 1. So this will be equal to 1 squared plus 1, which is 3. Again, if we plugged in 1, we would get 0 in the denominator, also in the numerator, so we can't do that. But we can try to rearrange things. This one's not factorable, but I see that the radical is in the numerator. So I'm going to rationalize the numerator by multiplying by its conjugate. So if it's root x minus 1, the conjugate would be root x plus 1 over root x plus 1. As I multiply this, root x times root x is just x. Root x times 1 is positive root x, and then you have minus root x, which we already know that we're going to get because we're multiplying by the conjugate. So then we have negative 1 times 1, and that is negative 1. So x minus 1 is in the numerator. We also have this binomial x minus 1 in the denominator and root x plus 1. I'm not going to distribute because looky here, that reduced. So 1 over root x plus 1. Now I can direct substitute and I get 1 over root 1 plus 1, which is 1/2. The limit as x approaches 2 from the right of x over x minus 1. To understand this graph better, I know that there is a vertical asymptote at 2, and I also know that there's a horizontal asymptote because the degree of the numerator is 1, the degree of the denominator is 1. So the horizontal asymptote is leading coefficient of the numerator over leading coefficient of the denominator, which is 1 over 1. So that horizontal asymptote is at 1. And I also know that a rational function with a vertical asymptote and a horizontal asymptote will either look like this or like this. This rational function is positive. There's not a negative in the numerator or in front of this fraction. Okay, so our branches are going to look like this. And if you wanted to test a value, you could go ahead and do that. But now I know that 2 from the right is approaching infinity. Discuss the continuity of this piecewise function. I know there's a discontinuity at 3, right? But I'm not quite sure what that discontinuity is, if it's a whole or a vertical asymptote. So I'm going to factor this and see if anything reduces. X minus 3, x plus 1. All right, it does reduce. Because of that, we have a hole at x equals 3, and that is a removable discontinuity. If g of x is equal to this, is a continuous function, find the value of a. So if this were to be a continuous function, that means when I plug in the transition value, which is 2, right, where we go from one piece to the other piece on the piecewise function, I need to get the same number out of both of these. I need the same output. So first I'll plug it into the bottom piece. 2 minus 3 is equal to -1. So I need the output of this piece to be -1 when I plug in 2 for x. So now I will solve for a. A is equal to -13. In order for this to be a continuous function, a has to be -13. Use a calculator to find these limits. So to begin, I want you to put this function in as your y1, okay? Ignore the limit part for now. Put this function into your calculator as y1. Okay, so now I've plugged it in, and I'm going to graph. At 1, it appears as though there's a vertical asymptote. On one side, we're approaching infinity. On the other side, we're approaching -infinity. So that limit does not exist. Here's the same rational function. They want to know the limit as x approaches 2. That looks like it might actually be a value. So I'm going to go to the table and see what it is. Second graph gets me to the table. And what is the y value? Error. So the table is not helping me. The graph is not helping me. So I need to go to the home screen. I'm going to go second, quit. And the number here that I'm approaching is 2. So what I'm going to do is I'm going to tell the calculator to tell me what the value is of this function when x is 1.999. In order to do that, I put 1.9999 into the calculator, and then I tell it to store, so press stow. I tell it to store that as the variable x. Enter. Now I've already put the function into y1, and I really don't want to type that all out again. So I want to tell it, hey, plug this x into y1. So now I'm going to go alpha, trace, and refer back to y1. Press enter. At this point, I press enter, and here is the y value at 1.9999. That looks to be about 1/3, but just to be sure, I'm now going to try 1.9999999. So I've stored it as my new x, and then I refer back to y1 using alpha, trace, enter, and it's giving me a number, even close to 1/3, right? These are turning into 3s. And you can keep estimating if you want to, but I feel pretty comfortable that this limit is approaching 1/3. Hey, remember the intermediate value theorem? If not, read through it. But hey, if f is continuous on the interval a to b, and k is any value in between f of a and f of b, then there must be at least one x value c between a and b such that f of c equals k. Maybe pause the video if you need to process that. But how do we test the intermediate value theorem? It's not too difficult. Does the intermediate value theorem guarantee a c value on the given interval? So the given interval here is 0 to 5, and they want to know if 12 is a possible output between 0 and 5. In order to find that, I will find f of 0, and I will find f of 5. And hopefully, one of those numbers will be above 12 and one of them will be below, and that will guarantee a C value. Ding, 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 0 and 20. 12 is definitely between 0 and 20, so yes. But here's the thing in calculus. In order to use a theorem, I must express the conditions. And the conditions are that f has to be continuous on the interval AB. So I must write that somewhere. Is f of x continuous? Yes, it is. Why? How do we know that? Because it's a polynomial. This must be stated to use the intermediate value theorem anytime on an AP test. Anytime you use a theorem, you must state that the conditions are there in order to use the theorem. So yes, intermediate value theorem, commonly known as IVT, so AP calculus readers will know that, guarantees a C value. On the interval 0 to 5, find the value of C in example 9a. So if one of the y values is 12, and we want to find the x value that goes with that, we will plug in 12 for f of x. 12 equals x squared minus x. I'm going to make this equal to 0 and try to factor to solve. And this does factor to x minus 4, x plus 3. So x could be positive 4 or negative 3. But they gave us a specific interval from 0 to 5. So which x value do they want? X equals 4. Or they said to find the C value. The C value is when x equals 4. C is equal to x equals 4. Oh, and guess what? I forgot to do number 9, part B. So does the intermediate value theorem guarantee a C value on the given interval? Well, this is a rational function. The interval they have given us is 0 to 3. I know rational functions do have discontinuities. So as long as these discontinuities aren't within this interval, then we're good to go. But x cannot equal 2. That's our vertical asymptote, and 2 is in this interval. So no, g of x is not continuous on 0 to 3, so we cannot use the intermediate value theorem.